Alright, we're going to start off by reviewing the exit ticket from last class. So this is our multiplication rule exit ticket. So let's do a brief review of everything, just the rules that we've talked about. So this is the probability of A complement, and it's the formula is 1 minus A, right? Because the complement is just the opposite of something. If I have the probability of A union B, it's going to be A plus B. That's it if they're mutually exclusive, but if they're not mutually exclusive, we need to subtract out the intersection of the two, because the intersection is what's being double counted. It's in both A and B. So it's in this number and in this number as well, so we need to subtract it out. And then the probability of A intersection B, we learned, is P of A times P of B if they are independent. We didn't do a lot if they were dependent. I'll go ahead and write that rule down, but there's nothing on this exit ticket about that. If they're dependent, it's the probability of A times the probability of B given A. So the probability of A times the probability of B given that A has already occurred. So this is for dependent. Alright, so looking at this is obviously a formula problem because it's given us probabilities, and it says what is A union B if A and B are independent. Alright, so it tells us A and B are independent, so I know that I can use this formula right here. Calculate A intersection B. So I know the probability of A intersection B is going to equal A times B. So 0.2 times 0.1. But if we read carefully, that's not what the question is asking us. It helps us get there, but the question is asking us about the union. So we need to look back up at this union formula. So the probability of A union B looks like it's going to be P of A plus P of B minus A intersection B. So they give us A, 0.2, they give us B, 0.1, and we just use the independence rule to calculate A intersection B. So I'm going to plug this in right here, minus the product of the two. And that gives me A union B. So for those of you that wrote E would be correct if they were asking for the intersection, but they weren't. They were asking for the union. So I need this, actually, which is B. 0.2 plus 0.1 minus the product of the two, because that's our union formula. So the tricky stuff about probability, like any other math, is that it builds up on each other. So we needed to know the independent multiplication rule in order to calculate this intersection over there. So although this was really a union problem, we also used aspects of the multiplication rule within it. All right, this one, a complex electronic device has 3 components. They give us the probability of failure for each component, meaning they won't work. If any one component fails, the device will fail. So I want you to answer these questions for me. Will the device fail if A fails? Yes. It said if any one of them fail, it all fails, right? So what if B fails? Will it fail? B only. I should say B. Sorry, 1 second. What if B only fails? Yes, it will fail. What if A and C fail? Yes, it'll still fail. All of these situations lead to the same outcome. If any one of them or any combination, as long as one of them is failing, the whole thing is failing. That will help us understand what the question's actually asking us for, right? Because it asks us, if the components fail independently of one another, what is the probability that the device will not fail? Well, we've got only one situation where the device will not fail, and that's if A does not fail and B does not fail and C does not fail. This is our only outcome where the machine is not failing. All three of them have to work. So, since it's an and problem instead of an or problem, are we multiplying or are we adding? All right, I hope you said multiply. So basically, we need to find the probability of each of these components not failing. We don't have that. We have the probability of failing, but ultimately we know that failing and not failing are complements of each other, right? So if the probability that A fails is 0.01, the probability of it not failing is 0.99. 0.03 is B failing, so we know 0.97, because they need to add up to 1 because they're complements, is not failing. And then what do you think about C? All right, for C, I hope you said 0.96. All right, so now let's go ahead and multiply this out in Desmos to see what we get. So I'm going to do 0.99 times 0.97. Oops, 0.97 times 0.96. When I multiply all of this out, I end up getting 0.921888, which is D when you round it to 3 decimal places. All right, suppose that A and B are two independent events with A and B respectively here. The probability of A intersection B complement is, all right, so that's a lot right there. So what I think we should do is talk about what this means before we do anything else. All right, we know it's an intersection, so we know we're multiplying. We know it's independent, so our multiplication rule would just be the two events multiplied by each other. All right, so once we've written out the formula, I think it's pretty easy to plug in the numbers. I have P of A, which is 0.2. P of B is 0.4, but I want B complement. So that's a quick, easy calculation you could do in your head, 1 minus 0.4. So that's going to be 0.6. When you multiply these two out together, 0.2 times 0.6, you end up getting 0.12. So C is your answer here. All right. All right, here's a challenge question. All right, so when a company is considering purchasing mineral rights to two different mountains, let's call them Mountain A and Mountain B. They look like normal curves. All right, so with these two mountains, we're considering purchasing the different mountains. The probability that if it will purchase the mineral rights to the first mountain, so P of A, so purchasing is 0.55. The probability it will purchase the mineral rights to the second mountain, P of B, is 0.4. All right, let's pull those numbers straight from the problem. Assuming the decision to purchase the mineral rights is made independently, good to know, what is the probability that it will purchase the mineral rights to exactly one of the two mountains? All right, so let me think about all the situations where I could purchase exactly one of the two mountains. I can only think of two situations. Can you think of what they are? Situation number one is that I purchase A and I do not purchase B. Situation number two is that I purchase B and I don't purchase A. All right, those are my two situations. I think I can figure out the probabilities of them using what they gave us. All right, so I know the probability of purchasing Mountain A is 0.55. All right, not purchasing B. Well, purchasing B is 0.4, so what would not purchasing B be? All right, they were complements, so it would be 0.6, 1 minus 0.4. All right, let's see down here. Purchasing B is 0.4, and then not purchasing A is going to be the complement of purchasing A, so that's going to give me 0.45. And all I did in my head was 1 minus 0.55. All right, so I've got these situations. Is this an and situation or an or situation? I'm looking at just number one right here. I need to purchase A or don't purchase B? Or do I need to purchase A and not purchase B? All right, I hope you said and, which means we're going to multiply these two. And is multiplication. And I can just multiply them straight away like this because they've said they were independent. .55 times 0.6 gives me 0.33. And then I'm going to do the same down here because I need to be able to purchase B and not purchase A. So I'm going to multiply these two, 0.4 times 0.45, which gives me 0.18. All right, so I've got my two scenarios here. What do I do with these two numbers? Let's take a step back and see what we're dealing with here. I've got one of two options for me to purchase exactly one mountain. I could do number one, option number one, or I could do option number two. So basically I just told you what to do with these two numbers with one word, right? I could do option one, or I could do option two. Since this is an or situation, to figure out the probability, that means I add these two numbers because or means add. So I'm going to do 0.33 plus 0.18. And I get 0.51, which is D. See, that wasn't too bad. All right, now we're dealing with the rest of the packet that we weren't able to get to in the live session, tree diagrams. So tree diagrams are used for multi-step conditional probability problems. So it's a conditional probability, but it's got more steps than what we're used to. Can you guys even read that? I have the worst handwriting. Multi-step, multiple steps. All right, a tree diagram helps us to see what's going on visually. I always, like, if you guys notice on that exit ticket, it helped me to just draw out my two scenarios of mountain A and mountain B, even though this really is nothing to me but a picture. So I always draw pictures or some sort of visual diagram, Venn diagram, to help you understand what's going on. All right, so your tree diagram, it shows the sample space of chance processes involving multiple stages. I told you it was a multi-step process. The probability of each outcome is shown on the corresponding branch of that tree. All the probabilities after the first stage are conditional probabilities. So this is basically like one of those choose your own ending books, right? If you go this way, these are your options. If you go this way, these are your options. But this is much more fun than a choose your own ending book. All right, true story here. Miss Lucas hits the snooze button on her alarm 80% of the school days. If she hits snooze, there's a 70% probability that she does her makeup before she leaves school. If she doesn't hit snooze and gets up right away, there's a 90% probability because I'm up, I'm on time, I got time to do the makeup. All right, suppose we select a school day at random and record whether or not she hit snooze and whether or not she arrived at school with makeup on. So we're going to go ahead and label our options here. So I could either snooze or not snooze. If I snooze, I could either put on makeup or not put on makeup. Same with not snoozing. I have the same two options. Makeup, no makeup. All right, let's add in those probabilities for each little branch. So what's my probability of snoozing? It looks like it's 0.70. Wait, no. Sorry, Miss Lucas hit snooze on her alarm 80% of the school days. Sorry about that, you guys. So I hit snooze 0.8% of the time. All right, use that complement rule to tell me what the percentage of me not hitting snooze is. All right, I hope you selected 0.2 because they should add up to 1. All right, now here is where the conditional probability comes into play. If I hit snooze, that's my condition, if I hit snooze. So I'm just looking at the top of this chart. I'm going to go ahead. All right, so if I hit snooze, there's a 70% probability that I do my makeup. All right, so what would my probability for not doing makeup if I hit snooze? Again, you're using the complement rule here, 30%. All right, now let's do the other side. If I don't hit snooze and I get up right away, there's a 90% chance that I do my makeup. So I'm going to put 0.9 here, which means what probability would go here? All right, I hope you said 0.1 because they're complements and should add up to 1. All right, so I've got 4 scenarios here. Snooze, makeup, snooze, no makeup, not snooze, makeup, not snooze, no makeup. Those are and probabilities because I'm snoozing and putting on makeup, or I'm snoozing and not putting on makeup. So with and, am I going to multiply or am I going to add? All right, I hope you said multiply. So with makeup, here I'm just going to take the percentages of the path that I followed. So if I went from snooze to makeup, I'm going to do 0.8 times 0.7. For this branch right here, I'm going to do 0.8 times 0.3. Down here, I've chosen the 20% path and then 90. So 0.2 times 0.9. And then down here, 0.2 times 0.1. If I've done all my calculations correctly on this tree diagram, these 4 options should add up to 1 because these are my only options in the morning, right? These 4 should add up to 1. So let's go ahead and plug them in the calculator, and then we'll add them up and see if we've done it right. So I'm going to do 0.8 times 0.7, and I get 0.56. All right, 0.8 times 0.3 gives me 0.24. 0.2 times 0.9 gives me 0.18. And this gives me 0.02. All right, let's add all these 4 numbers up and see if I get 1. All right, I do, so I know that I did it right, because these are all my possible outcomes. All right, now let's take a look back at the question and see what was the probability they wanted. So suppose we select a school day at random and record whether or not they hit and whether or not she was at school. Oh, there is no question yet. Okay, so let's look at part A. What is the probability that Miss Lucas hit snooze and doesn't wear makeup? So I hit snooze, but I didn't wear makeup. So that's my number right here. P equals 0.24. I hit snooze and I did not wear makeup. All right, what is the probability that Miss Lucas does not wear makeup on a given school day? All right, so here I've got 2 different options, right? I could have done snooze, no makeup, or I could have done no snooze and no makeup. You notice that word or. I could have done snooze and no makeup, or no snooze, no makeup. So that word or means that I'm adding. So let's go ahead and find these 2 probabilities. Snooze, no makeup was 0.24. And then no snooze, no makeup, 0.02. When I add these 2 together, I get 0.26. All right, suppose Mrs. Lucas didn't wear makeup on a random school day. What is the probability that she hit the snooze button that morning? All right, suppose I did not wear makeup on a random school day. So we're going to say that's my condition. No makeup. So my fraction that I set up should have my no makeup total as the denominator, which we actually already calculated, right? Here's my no makeup total. I could have done snooze and no makeup or no snooze and no makeup. So my total is right here, 0.26. What is the probability that she hits snooze? So which one of these 2 numbers should be my numerator? All right, 0.24, because that's me hitting snooze. All probability is just setting up the fraction correctly and then dividing. So let's go ahead and do that. 0.24 divided by 0.26. And I get, I'm going to round to 2 decimal places and get 0.92. And that makes sense. Look, snooze and no makeup is 0.24 compared to no snooze and no makeup, which is tiny, 0.02. So 92% of the time I've snoozed if I'm not wearing makeup. All right, let's get some practice with some practice AP problems. All right, give this one a shot on your own. Try and create the tree diagram and then see if you can use it to solve the question. All right. So let's see. I'm going to draw the tree diagram just like we did before. All right, 90% of people who have a particular disease, so let's say disease, no disease. Okay. So 90% of people who have the disease, 90% of people who have it will have a positive test result. All right, so I can use my complement rule to figure out the negative test result. And that's all this is just like a puzzle where we need to fill in the missing pieces. So if 90% of people who have the disease have a positive test result, that must mean 10% of the people who have the disease get a negative test result. All right. 90% of the people who do not have the disease, all right, so again, 90% of people who do not have a disease will have a negative result on the test. All right, so that must mean that 10% will have a positive result. All right, if 5% of a certain population has the disease, all right, that must mean, using the complement rule, what percent of the population does not have the disease? All right, 0.95. So all this is just mapping out the diagram and using the complement rule to fill in the missing probabilities. So I've got my tree diagram now. I just got to figure out what the scenarios are. I guess I should multiply straight across to see what each of these outcomes are. So disease and positive test is going to give me 0.05 times 0.9. Disease and negative test is 0.05 times 0.1. No disease and negative test is 0.95 times 0.9. And no disease and positive test is going to be 0.95 times 0.1. So let's go ahead and calculate these. And remember, the check to make sure that I did this right is I'm going to add up these four and they should sum up to 1 because this is my entire sample space here, right? Every single possibility is included in here, so they need to add up to 1. All right, so I'm going to go ahead and add those 4 numbers up. And that's just a check to make sure I did everything correctly. Yep, it works. They all add up to 1. All right, so I know I did it correctly. All right, let's see what the question's asking. What percent of the population would test positive for the disease? All right, so a positive test is here, and a positive test is here. So I could have this situation or this situation. So since this is or, meaning I could have positive here or here, I'm just going to add them together to get my final number. So 0.45 plus 0.95 should give me my final probability. 0.045 plus 0.095 gives me a total probability of testing positive of 0.14. So D is the correct answer here. So remember, we multiply to get across because it's an and situation, disease and positive test, disease and negative test. And then we add at the end because these are all 4 of my scenarios, so a positive test result would be this or this. All right, go ahead and pause the video and try and do the next one on your own. right. So it looks like for flights from an airport in January, there's a 30% chance of a flight being delayed because of icy weather. All right. If a flight is delayed because of icy weather, there's a 10% chance the flight will also be delayed because of a mechanical problem. All right, so I guess we've got icy delay and no icy delay. Then we've got mechanical delay, no mechanical delay. Same here. And I know which one came first because of the way that the question's worded. It says, if a flight is delayed because of icy weather, there's a 10% chance the flight will also be delayed because of a mechanical problem. So that's why icy delay comes first, mechanical delay comes second. So no mechanical delay. All right, so I've got all my options here. I just need to fill in the probabilities. So it looks like 30% chance of icy weather delay. So that means 0.3 is here. So you can tell me what this would be here. 0.7 because they're complements. All right, if a flight is delayed from icy weather, there's a 10% chance of a mechanical delay. So that means 90% no mechanical delay because those are complements. All right, if a flight is not delayed by icy weather, there's a 5% chance that it will be delayed because of mechanical problems. So I'm going to put 0.05 there, which means the complement would be 0.95. All right, now let's go ahead and multiply across to get my 4 scenarios to make sure we did the calculations right. 0.3 times 0.1, 0.3 times 0.9, 0.7 times 0.05, and 0.7 times 0.95. All right, I'll go ahead and put those in the calculator. And remember, I check myself by seeing if they add up to 1. All right, so it's going to give me 0.03, 0.27, 0.35, and 0.665. All right, so there are my 4 probability outcomes, and I'm just going to add them up. Yep, and they add up to 1. So I know I did it right. Okay, let's see what the problem says. If one flight is selected at random, what is the probability the flight selected will have at least one of the 2 types of delays? So at least one means it could have more than one, right? So at least one of the delays. Here I've got both, but that's included because it has at least one. Here I've got icy delay, so that's included as well. Here I've got no icy delay, but I have a mechanical delay. That's one of them. And then down here is no delay, no delay. So I don't need to worry about this last one. I'm just including these top 3. So these are my 3 situations. I could have this or this or this. Since it's or, we're adding. All right, so once we add those 3 together, that should give us our final answer. And it does. The final answer is 0.335. Let's see if that's listed out in our answer choices. It is. Answer choice B. All right. Let me know if you have any questions.